Boaz Klartag from Weizmann Institute and Tel Aviv University will tell us about lattice packing.
Thanks, Enon. And also thanks to Irit for inviting me to speak here. So indeed, I will talk about the lattice packing and field packing. And just before I start, I would encourage you to stop me at any time and ask questions or make comments if something is not clear. Okay, to make it talk better if you interact. Hi, Peter. Hi.
Yeah, my hearing is not so good. Talk about that.
Louder.
Louder. Okay. So I'm going to talk about sphere packing. So what is sphere packing? A sphere packing in Rn is just a collection of disjoint Euclidean balls, all of the same radius. So in this lecture, you can assume if you want that all balls have radius 1, just a collection of balls for radius 1 as a part of disjoint, and my balls would be open, so without a boundary. Now, if the sphere packing is reasonable, then it has a density. What's the density of a sphere packing? So you can take a large box, you can measure the proportion of the volume of the box that is being covered by the balls of the partition. And usually, if you let the box tend to infinity, this proportion of the volume of the box that is covered tends to a limit, and that limit is called the density of the sphere packing. So it's the proportion of total space that the sphere packing covers. And in this lecture, we are interested in the maximal density of a sphere packing in Rn. This is a separate question for each n. Let's begin to discuss the Palmer case when n equals 2. So in this slide here, we can see an example of a circuit packing. There's a circuit packing. Okay, and the actual circuit packing that I have in mind extends periodically indefinitely in all directions. Okay, this circuit packing is called the hexagonal circuit packing. And why is that? Because each circle has 6 neighboring circles. And if you look at the centers of these 6 neighboring circles, then these are the vertices of a regular hexagon. Okay, this is why it's called the hexagonal circuit packing. The density of this hexagonal circuit packing is pi over root of 12, so roughly 91% of the volume of the area of the plane is covered by circuits of this packing. And it was shown a long time ago by Lagrange and rigorously by Thun and Ferstos that this is optimal. So this is the best density, the maximum density of any sphere packing in the plane. Okay, of course, that's not okay. One more thing that you can see about this circuit packing is that the centers of this packing have lots of patterns. You can see lines and parallel lines. And in fact, the collections of centers of this circuit packing is a lattice in the plane. Okay, and what's a lattice? A lattice is the linear image of Z2 of the integer vectors under a linear map, which is invertible. Okay, so here we can see that it's actually a lattice. The linear transformation here is probably a shear transformation. So it, let's say, keeps the x-axis and it moves parallel lines, let's say, to the right, and very proportional to the distance from the x-axis. You can get this lattice. In general, any lattice has an important invariant called its covolume. The covolume of a lattice is the volume of the fundamental cell, or if you want, it's the absolute value of the determinant of this linear map T, the image of Z2. There are many linear maps T that lead to the same lattice, but the absolute value of the determinant is an invariant. It does not depend on the lattice, right? So this is the hexagonal circuit packing. What else I can say? The colors mean nothing in this picture. This is just for beauty. If you can see, so you can see that there are holes in between the circles, and if you count carefully, you could see that there are roughly twice as many holes as there are centers in this hexagonal lattice. Okay, so this is about the case, the two-dimensional case. And when I say a lattice sphere packing, I mean a sphere packing where this collection of centers form a lattice in Rn. Okay, and lattice sphere packings seem to be slightly easier to construct or to analyze the general sphere packings. In particular, in all dimensions where we know what is the optimal density of a sphere packing, there is a lattice sphere packing which attains this optimal density. Okay? So dimension 3, let me say a few words about dimension 3. In dimension 3, there are two different lattices that attain the optimum. The optimum is this number, 74% roughly. These lattices are, okay, called FCC and HCP. And I mean, it goes back to the work of Kepler and Gauss and pursued rigorously by Hales at the end of the 20th century. And using it was a computer-assisted proof that was later verified. One nice thing is that there are many materials in nature where the atoms are arranged according to one of these lattices, the FCC and the HCP. And kind of many materials choose one of them as a way to arrange the atoms, but there is a material called cobalt which actually chooses both of them. So how does it work? Cobalt has a phase transition at roughly, I think, 700 Fahrenheit. So below that temperature, the atoms are arranged according to, I think below that is the HCP lattice. And then at that temperature, there is some density of the atoms. The volume does not change because they have the same density. And they are arranged above that temperature. It is still a solid, but they are arranged in different manner. How do you construct these two lattices, the HCP and the FCC? There are many ways to construct them. Let me explain how to construct them given the hexagonal certain lattice. So you pretty much do the following. You have layers. Each layer of this, both of them will be just the hexagonal circuit packing. And you take a layer and you want to fit the next layer in the holes in between the circles of not the circle, the balls. You have a layer of hexagonal circuit packing and you want to fit the next layers in the holes of between the balls in the previous layer. If you have just two layers, everything is equivalent up to rotation. But now when you put the third layer, you have two options. So you can either have, you can either go back to the original arrangement, or you can, so there are twice as many holes as there are circles. So either go back to the first one, or you have one bit of degree of freedom. You can have a different arrangement, and this is the difference between HCP and FCC. So this is about the case n equals 3. Dimension 4, 5, 6, 7 is not known, but in dimension 8, there is a remarkable object called the E8 lattice, which is as nice as the hexagonal lattice. It's a lattice with a large group of symmetries. Many isometries preserve the lattice. It has perfect kissing. So if you look on a single ball and look at its neighbors, it's a tight arrangement, unlike the case in dimension 3 and like the case in dimension 2. And Blichfeld proved that it's the optimal among all lattices, and then Vyazovska in 2016 proved that it's the optimal among all sphere packings. So now we know that in dimension 8, we know the density of a sphere packing. Now, my impression is that at the time of Blichfeld, the sphere packing problem, the lattice sphere packing problem, were very theoretical questions in number theory related to quadratic forms. But more connections were found in 1940s and 50s thanks to the advancement of computers and communication and error correcting codes and digital coding. In particular, there is a model of communication from Shannon called Gaussian channel. And when you want to transmit digital messages, you want to find vectors in Rn that correspond to these messages. And the noise is in L2, so you want them to be as far as possible, the messages in terms of the L2 distance, in terms of the Euclidean distance. And as part, so you want basically to find a sphere packing or even a lattice sphere packing to consume messages. And so this problem acquired new connections, and there's also connections to group theory, to finite simple groups. And John Lynch, the mathematician John Lynch, discovered in 1965 a new remarkable highly symmetric object in dimension 24. Okay, this is called the Lynch lattice after John Lynch, and this lattice that Lynch found was shown to be optimal by Vyazovska and Quarters, Kohn, Kumar, Miller, and Radchenko 1 year after the dimension 8 case. Okay, so in dimension 24, we know that the density of a sphere packing is this number, which is the volume of the unit ball in 24 dimensions. Okay, or if you want, it's roughly 1/500. Now, there are two opinions about this number. Yes, yes. No?
Is it the minimal among all lattice sphere packing or among all sphere packing?
All sphere packing. So thank you. So this slide among all sphere packing. I don't assume lattice. If you want to assume lattice, more is known. Be in the next slide. But this is the best among all sphere packings. Okay. More questions?
What is the difference between the bar and the
Yeah, that's exactly. Yeah, that's this is for delta is for lattice sphere packing, and with the bar is the bigger number, which is density of general sphere packing. Okay. We don't know if a single examples are different, but it is conjecture that Rogers conjectures that they are different in high dimension. Let me just say one word about this number. So is it a big number or small number? So you see the density goes down in dimension. So you can think it's a small number, but actually, when I was surprised that this is a too large number because this number is the volume of the 24-dimensional unit ball. In my mind, the unit ball in n dimension is a tiny volume. Its volume is 1 over root of n to the n. So it decays like faster than exponential. So I would expect 2 to the minus 24, even more, less than that, like 1 over millions. But no, so it's a bit larger, so because the asymptotic of the volume of the unit ball takes time to materialize. Okay, so this one dimension 24. Now, let me not to forget, so I have confused notation. So delta n is the density of a lattice sphere packing. Let me just put it on the board. And delta bar n, which is a priori larger, is n sphere packing. Okay, so I have two parameters. I'm not confused between them. Okay, and there are more bounds that are known. There's a trivial lower bound for delta bar, which is at least 2 to the minus n. So why do we know that we always have a sphere packing with density, any sphere packing, not a lattice, is density at least 2 to the minus n? Just take any maximal sphere packing in Rn. Just apply if you want the greedy algorithm. Just add the balls one by one as long as you can, and you stop if you just cannot. So if you cannot add one more ball, what does it mean? It means that all points in Rn are of distance at most 1 for one of the balls, because as always you can add a ball, or if you want all the balls in Rn of distance at most 2 from a center. So if I blow up the balls by a factor of 2 to recover everything, so after you blow up by a factor of density at least 1, so before it was at least 2 to the minus n in n dimensions. That's an obvious lower bound. Okay, what else is known about these numbers exactly? So if you look at the case of a lattice sphere packing, then you can determine the numbers also in the intermediate dimensions, 4, 5, 6, 7, and recently also 9 in the computer science proof. We're checking billions of local minima. So these numbers are known. But basically that's it. So even in dimension 10, I don't think that even the lattice packing is known. There are many, there is a collection of articles in a book by Conway and Slow, many conjectures and bounds for delta n. Physicists are also interested in this problem, and Parisi and Zamponi looked at, for example, they did many things. In particular, they looked at statistics of some tables for the optimal and conjectures about delta n up to dimension n equals 50. And they wrote that if you look at, okay, first of all, it's pretty common to scale delta n and delta bar n by 2 to the n because of this bound. So they look at this after you scale by 2 to the n. They think that the statistic shows that this goes exponentially in dimension n. But then they write, they're very cautious, they write that it could be that what they see in the statistics is a pre-asymptotic effect. So, for example, we said that even the volume of the ball, 24 dimensions, is too big because the asymptotics in high dimension takes time to materialize. So maybe even dimension 50 is not good enough for that. Okay. Yes.
For example, the equality between delta and delta bar.
Not
It
now.
can be conjectured in dimension 4. It's not true. Or is that something you said it in high dimensions? Conjecture not true.
I don't quite know. So Rogers wrote in an odd paper that the conjecture was that in some dimensions delta n is not equal to delta bar n. I did not see any written conjecture about delta and delta bar in dimension 4. So I just don't know what is conjecture for in this case. In the physics literature, I'll talk about it later on. So there are many. It seems that and my impression is that the physics literature on this problem did not reach a consensus also. So you can find there is a several papers saying about it. So I'm not completely sure what's the value of conjectures exactly in this right now. Okay. 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 Just one more thing. So I told you that we like to scale delta n by 2 to the n. In fact, this is another notation that I want to add to the board, so we don't forget. So it's common to capital delta n by 2 to the n times times delta n. And one reason for this is that this has a geometric meaning. Okay, so 2 to the n delta n is the largest volume of an ellipsoid in Rn, center of the origin, which is integer free. Integer free means that it contains no integer vectors except for the origin. Okay, so we have I have my integer lattice, and this is integer lattice, and my goal is to find a large ellipsoid that is integer free, contains no lattice points other than the origin. And why these two things are the same? Why the delta is the same thing? Because if you take any lattice L, if you have lattice packing, it means that after you scale the board by a factor of 2, it does not contain any lattice vector except for the origin, and a Polynomial transformation, transforming balls to ellipsoids. Okay, so this is a little lemma, and the question is basically finding large ellipsoids that contains no integer points except for the origin. Okay, and for instance, if I look at one contender in this optimum is just the unit ball. The unit ball, since I look on open balls, the unit ball has no integer points in its interior. But it's a very weak contender because, as we said, its volume in high dimensions is tiny. Okay, the volume of the unit ball in n dimensions is roughly the volume of the unit ball is roughly root of 2 pi e over n to the n.
So all your intuition in high dimensions is Stirling's formula, or you actually have an intuition?
What?
You have an intuition in high dimensions, or it all just comes from Stirling's formula?
Of course, I mean, unit cube is volume 1.
No. I'm saying
You have many, I mean, the unit cube is way larger than the Euclidean ball.
I'm saying when your intuition
Yeah,
comes from this computation of volume.
no, intuition comes from the fact that if the cube is volume 1,
Yeah,
the cube for me is like a ball of square root of n.
Yeah.
Why? Because if you take 2 points in the ball, the cubes are this is root of n. So for me, okay, you can look at the same formula, but actually you can see that the cube is way larger than the ball. The cube is like root of n, so it kind of means that the unit ball. Yeah. No, there are many ways to form intuition. Okay. Anyway, so it's not clear how to find a good. So this is not a good contender. So you need to find a crazy ellipsoid kind of that is stretched in some directions to have an ellipsoid of large volume. Avoid all integer vectors, okay? So it's not very obvious, but Minkowski and Hlawka were able to find such an ellipsoid, and theorem says that capital delta n is at least 2, okay, plus some change. So you can find somehow an ellipsoid which is very different from the Euclidean ball that has a volume at least 2. But it's very hard to form intuition in high dimensions. And the proof by Minkowski that we actually will see, it's a very simple proof, it's a probabilistic proof. And nobody knows how to have an explicit construction of an ellipsoid in high dimensions. The volume is not even 2, even much smaller than that, even e to the minus root of n, I think it's not entirely known. So and there is an open problem by Peter in his list of open problems in number theory from the year 2000, it's problem 10. Problem 10 in this list is to find an explicit construction. Okay, you guys do the randomization, no? Can you, no? Okay, how's this now? Okay, yeah, so if you can de-randomize and find an explicit construction of any ellipsoid that is integer free in high dimensions and goes to 0, not so, let's say 1 over log is okay. So, okay, good. Anyway, now, this was Minkowski's boundary, I explained, then it was improved by Rogers in 1947.
One point, it's very interesting. Minkowski's bound comes from his mass formula, which is a strange formula, which it's not clear why he's averaging. But the formula, there's so many inequivalent forms in the genus of this form that he's really averaging over all the lattices. That's not usually pointed out, but he didn't average over. He just wrote down his mass formula. No, he wrote his mass formula, which is an average over the genus, but the genus grows like n factorial, the class number of the genus. The class number of the genus.
So, okay. So I did not, so okay, what I, okay. So
Hlawka average.
Hlawka's paper is
He didn't call it half measure. And people.
But it's the half measure of the right. But Minkowski did this only on.
Using his mass formula for quadratic form.
Okay, thank you, thank you. I just explained the classical proof. Okay, Rogers did a constant time set. I also explained Rogers proof. Rogers used Minkowski's second theorem, successive minima, for improving this by a factor of n. And along the years, there were improvements of the constant. Rogers got 2 over e and then Davenport 1.67. Then Schmidt gave, it's a very nice paper where he analyzed kind of large events that are pretty rare with very small probability and introduced some Poisson heuristic for this problem, which is very useful. Then Keith Ball in 92, he proved that C is roughly 2. And for that, he used another type of averaging. He used the Bank solution of the Tarski's Planck problem. Let me tell you, a Planck is the region in space between two hyperplanes. That's a Planck. And the Tarski problem was to show that if you cover a convex body but by finitely many Plancks, the sum of widths of this Planck is at least the minimal width of the convex body. So this is true, and it was used in Ball's proof. Then in 2011, Stephanie Vance, she showed that this constant is at least 6 over e, which is more than 2, but only dimension divided by 4. And she used, why this is important? Because she used quaternionic field and only, she only averaged over lattice with quaternionic symmetries. So this enables you to improve the constant. Then Venkatesh in 2013, he took this idea of looking only on specific dimensions and really improved it by significantly. He used more sophisticated algebraic symmetry cyclotomic fields. And he got a very large constant in high dimension. And also, he got that among a subsequence of dimensions, you can get a log-log factor. This was an improvement. And this constant was improved to 1 by Gargav and Vyazovska 2 years ago. Okay, and Venkatesh also formulated a conjecture. So he wrote that this capital delta n, the volume of the largest ellipsoid, which is integer free, grows at most polynomial dimension n. So this was his conjecture, okay? And I'll discuss some reasons to believe or not to believe in this conjecture. I'm a believer. Okay. Now let me just say what's known. Let's finish so what's known about non-lattice field packing. So let me write delta. Okay, so this is the last notation. I promise. No more. This would be 2 to the n times delta bar. Okay, so I scale everything on the. So for non-lattice field packing, you have to scale by 2 to the n. Okay. So there was a proof by Krivlevich, Litzin, and Vardy from 2004. They reproved the bound by Rogers using another method. Then the physicists, Parisi and Zamponi, they made investigations using the replica method about the field packing high dimensions. The replica method is a highly successful theory in physics, and Parisi got the Nobel Prize for it, but it's a non-rigorous method. Okay, and they wrote quite carefully, but wrote that in some scenario, under some assumptions, you could suspect that delta bar n could be n log n times 1 plus a to the power of 1. Okay, but this is just one scenario, and they started. So it seems the interest of physics in the problem, and there are many follow-up papers on field packings. And as far as I understand, they did not reach a consensus. There is a survey paper describing certain scenarios and what would happen in each scenario. Basically, I mean, scenarios cover all possibilities more or less. Okay, but in the early papers, this was the scale that was mentioned, n log n.
Was
Yes,
equal or greater or equal?
equal. So
They conjecture.
they're conjecture. It's not. They did not conjecture anything. The kind of this is the only scale they mention, and under some scenarios, if the glass phase and they say it should be an amorph. Yeah, I would not call it a conjecture. So okay, Zamponi later wrote a survey paper in which it was more clear what's going on. So there are 3 scenarios, A, B, and C. Scenario A is that this is the right answer, n log n. Scenario B is polynomial growth, so n to some. Okay, it's a bit funny. It's n to the psi times log. So psi is a constant which different papers have different opinions about this, but log cube is completely certain. And there is scenario C, which is exponential improvement. This paper is about the fate of in high dimension. Okay, but it's really, I mean, I could not find my hands and legs in the physics.
But is that a psi? They give a number psi? What's psi?
Yeah, so they don't. So this is scenario B in the scenario B, and in scenario B, it's split into several scenarios with different psis. Okay. So psi is not a completely little. Okay, so we're laughing because we're mathematicians, but these people are serious people and they have serious work.
Well, we're laughing because we're looking at the theorem at the bottom.
Okay. then a mathematician, Campos, Jensen, Michelin, Sasser, Buddha. So they were influenced by the work of present and Polynomial. They take the amorphous packings, and they almost proved the prediction of this prediction. So they proved that delta bar is at least half times n log n. Okay. So this was the first deviation, if you want, in all dimensions. Like if the Venkatesh was in subsequent, this was in all dimensions n log n. But it turns out that and this was a non-lattice field packing. Okay, but it turns out that recently we were able to show that it goes at least like n squared. So we can find ellipsoids that are of volume n squared that are over integer points. Okay, and if you believe in the Venkatesh conjectures, then the next step would be to say what is the exponent, and I can give you reasons why n squared is a reasonable guess.
Yeah, when I wrote that conjecture, I told the truth.
Ah, you're here. Good not see you. Hi.
Hi.
Okay.
No, just to make your theorem more impressive. When I wrote that conjecture, I thought the truth was n squared log n.
To the cube? Okay.
Yeah, okay, n squared times a log power. So your theorem is as much as it would have been.
Okay. Yeah, maybe. I share your belief. But imagine, I'll explain what is my explanation. Yeah, okay.
Some reasonable number.
In this theorem, so first of all, it's effective, so you can get some constant from the proof. I did not compute it at all. We can simulate in the proof is kind of semi-algorithmic, randomly algorithmic, so you can simulate and see what you get. And the physicists do have some project for computer simulations, so they'll at least announce some constant, I hope so. But I don't know that. Okay. Let me reformulate this in, okay, you can reformulate it in a slightly different way. So if you have a Euclidean ball in Rn, whose volume is at most n squared, then you can find the lattice of covolume 1, which avoids all points of this Euclidean ball, except for the origin. Okay, that's another way to reformulate this theorem. And why do I formulate it in this way? Because for some people in the audience, the letter K reminds of a convex set, maybe in German. Convex set. Okay, so the conjecture is that Euclidean balls, at least up to a constant, should be the hardest to pack. So if you have any centrally symmetric convex body, maybe this is also true, that you can pack them with the same density. I don't know if it's true. Schmidt, in his 63 paper, proved this under the Winkler assumption of volume n squared, n, not n squared. So, okay. So that's a conjecture right now. Okay, so all of this was about constructions, lower bounds for strip packing. What about upper bounds? So there is a really very, very nice paper, 4 pages by Blichfeld in English from 1929. It's really a proof of book where he shows that there is a non-trivial upper bound for the density of any sphere packing in Rn. So it's not to the minus n, but roughly to the minus n over 2. Okay, so it's 0.71 to the n. Okay, it was kind of a precursor for the later linear programming bounds that appeared later. Although linear programming was not officially invented at that time. Then there were concept factor improvements by Rakin and Rogers, and then Kabatiansky and Levitch improved the exponents. They got 0.60 to the n, not 0.71 to the n. And then there were improvements by constant factors by Kohn and Zhao and by Sardar and Sargar. But you can see that there is still a huge gap between the upper bound and the lower bound in this problem. Okay, so the upper bound is 0.66 to the n, the lower bound is 0.5 times some correction. I have no opinion about delta bar n, but about delta n, it's an easier problem for that. That's one. Let me give you some arguments whether you could conjecture exponential or polynomial growth for the instance of a lattice sphere packing. So some reasons for the exponential is that the statistics, if you look at the graphs, you can't go. This is clear. Also, there are some lattices in Rn that are too good to exist, not for sphere packing, but for different problems. For example, for the kissing number. The kissing number is you want to have a Euclidean ball that touches as many, let's say an ellipsoid that is integer free, but has as much as possible integer vectors on the boundary. Okay, that's called the kissing number. And random constructions like in this thing would give you n square for n square log n, but you can have algebraic constructions which are super polynomial into the log square n, the bounds for lattice. So there are some things that we don't understand about lattices, so maybe the same thing would go for the sphere packing. And there are some analogous problems on finite fields for large Q for which you can get exponential improvement. So if you have some L-correcting codes are way better than the Gilbert-Rashomov bound. But not for F2, for Q equals 2 it's not true, but for large Q it's. Okay, so these are some arguments in favor of exponential improvement of delta n. Now let me give you maybe, and actually could correct me, some reason why can you believe that it's only polynomial. So my explanation, maybe it's wrong, is that if you look at this function lambda 1, the length of the shortest vector of a lattice, that's pretty much what we do, right? So this is a function of the space of lattices, and the decusp, it's kind of irrelevant. So the cusp, this function goes to 0, so it's not, we want to find its maximum. So this means that for sphere packing, pretty much you want to find a lattice which kind of in the bulk of the space of lattices, where kind of a random lattice more or less belongs. And then, if you believe that random lattice is roughly what you need to look at, then you can discretize the space of lattices. It has dimension n squared. So maybe you have, e to the n squared log n different points in the discretization. And this function lambda 1 is kind of has some exponential law, basically. So you have e to n squared log n experiments, and the best of them should be roughly n squared log n, basically. If it's kind of typical random function with many local hills, and you just get some one of the hills happen to be a bit above the others. Okay, that's one argument for the polynomial volume. Okay, just not. Okay, thanks. Okay, now this is all about the results. Now let me tell you a few things about the proofs and the ideas at least. Any questions about the story of sphere packing, the results? Okay, so now let me switch to discuss proof. So how do you prove something about lattice sphere packings? So let's look at the space of lattices. We call it Xn. This is the space of all lattices of covolume 1 in Rn. Okay. So lattices can degenerate. You can find lattice of volume 1, which has vectors which are very close to 0. So it's a non-compact space. Okay, but still it's like a manifold dimension n squared minus 1. Yeah, n squared minus 1. And it's a homogeneous space. Okay, so you can apply a linear function of element 1 or minus 1 and get another lattice of covolume 1. Okay, so and it's a transitive group action, of course, because each lattice is a linear map. So when you have a space with a transitive group action, it has a Haar measure. Okay, so you know that there is a certain measure on this space, which is kind of which is invariant under the group action. But it's not entirely clear what's the total, at least a priori, and before you think, if it's going to be an infinite or finite measure, right? I mean, the space is non-compact, so you could, it's not clear at all. But Minkowski was able to compute the volume. I mean, Minkowski and, let's say, and Ziegel also, they I hope it's true that Minkowski was okay. Minkowski and Ziegel discovered that the total measure is actually finite. Okay, Minkowski definitely computed the volume of the space of lattices in the product of zeta function. So apparently it's not at all obvious, but there is a unique Haar probability measure on the space of lattices. So there is a canonical way to sample a random lattice of covolume 1 in Rn. And it's quite an impressive measure when I just learned about it, I mean, really a few years ago. I mean, kind of really, I mean, yeah, it's a nice thing that we can flip coins and get a random lattice in Rn of covolume 1. It's not entirely clear what this is. And the nice thing is that the distribution will be invariant under Euler transformations. Okay, so this is really quite a canonical object in mathematics. And just the fact that there is such an invariant probability measure already has lots of consequences. For example, you have the Ziegler summation formula. Okay, so all we know is that we claim that there is a Haar probability measure on the space of lattices. We don't even tell you just this fact. There is a pointer. Then let's get the Ziegler summation formula. So let L be just a random lattice, random uniform distributed lattice of covolume 1. That's the uniform measure. So I claim that for any test function in Rn, continuous complex ordered function, if I sum my function over the non-zero lattice vectors. This is some random variable because it depends on L. If I take the expectation, it will be exactly the integral of f. So why is it true? Because of this invariance of this random lattice L. What happens if I take the function f and compose it with some SLN map? Then each lattice, the sum could change, but we know that I can move the map to the lattice L and it's fine. So we know that the left hand side will not change. So it means that this thing is an SLN invariant functional on the space of continuous function on Rn. And the ansatz mainly reasonable functional on this space. It's basically the value at 0 and the integral and some linear combinations. So you rule out the value at 0 because you don't sum over 0. And all that remains is pretty much the integral times some coefficient. And just by kind of scaling, you see that the coefficient has to be 1. So this formula is this intuitive. Intuitively, it's not very hard to believe in it or to prove it, just from the fact that you have a unique probability measure on Xn. And now let me prove for you the Minkowski bound in 3 lines or 1 line, depending how you count. How can you prove that there is a lattice of covolume 1 which avoids a Euclidean ball of volume 2 or let's say 1? Euclidean ball of volume 1 is huge, right? It's radius root of n. Euclidean ball of volume 1 is volume root of n. And how could you avoid this ball? Okay, so let's do the following trick. Let's just take random lattice L and count how many non-zero vectors it has inside B. B is the ball of volume 1. Okay, so this is a random variable, which is integer value, then or negative. You just express it as a sum over the lattice, non-zero vectors of the lattice of the indicator function of B evaluated at the point. But this is exactly what you have in the Ziegler summation formula. It's 2 in L1, by the way. Don't need to go continuous at all. I just told it. So you can apply easily this function in this Ziegler summation formula and get that, okay, I can replace this thing by an integral. But integral of the indicator is just the volume. So I get that the expectation of this integer value, the non-negative random variable, is at most 1, okay? So by the probabilistic method, the first moment method that was coined 50 years later, you understand that this random variable has to vanish somewhere. It cannot be always at least 1. If it vanishes somewhere, it means that you have a lattice L that has no points from this unit ball B. So this is the Minkowski-Hlawka proof, okay. That's why this is the bound of Minkowski-Hlawka. Now let's move on to the Rogers proof to 1947. So how did Rogers improve by a factor of n the Minkowski bound? Rogers actually wrote in one of his papers that some statistics reminds him of a Poisson distribution, which he learned from some economist. And indeed, this is true. So what we kind of understand from the Ziegler summation formula is that certain statistics of a random lattice in Rn reminds us of those of a Poisson process of intensity 1 in Rn. So a random lattice will give you just random collection of points. And if you are thinking on a fixed dimension 2, for example, this looks like a very structured set of points, okay? But apparently, it's most pronounced in higher dimensions. You can just think of it as some random collection of points. And it turns out that if you have events that do not involve more than a linear number of the points, then it's pretty much the same answer as you would get if you just saw the points randomly, but with density 1, just a Poisson process. For example, in this theorem, it remains true if instead of having L to be a random lattice, you take a Poisson process with density 1, the same theorem is true. Of course, what would be the average of the sum over the Poisson process of the function? Just the integral, what could it be? Okay, so, and this is a good point kind of for understanding random lattices. Let me repeat it. If you have an event that does not involve more than, let's say, n-1 of the points, pretty much you'd expect that the answer would be not so difficult from what you get from a Poisson process. And Poisson processes are really easy to analyze. I mean, basically, you can answer questions about Poisson process intensity 1 are much simpler than questions about random lattices. So that's the philosophy. Now, let's for example, let's implement it in the following case. So we have a lattice L of covolume. Now I want to renormalize covolume will be the volume of the unit ball. So that the shortest vector will have length 1 roughly. Let's enumerate the vectors of L according to increasing distance from the origin. So the points are x0, which is 0, then x1, x2, etc. And these points are tending to infinity, and each one of these further from the origin is the first. And let's look at the first n shortest n vectors of this random lattice. Okay, then its probability at least 1/2, or even more than that, typically. for Poisson process, it's easy to compute, but also for random lattice, it's not so hard to compute. And Rogers did it. The product of the length of the first n vectors is at least n. I mean, if you okay, you can see for yourself what you expect for the assignment and see that this is indeed true. Okay, and now you're just pretty much done. Why are you done? Because of the Minkowski second theorem, this one on successive minima. So this is a deterministic theorem, kind of something that you could learn in an undergraduate class, which says that for any lattice L, or if you want for any lattice L, if you look at the let's say the n shortest vectors, which are non-zero in this lattice, then you can find a linear map T of the time that is at least this product, such that the ellipsoid, which is the image of the unit ball under T, does not touch L at all, does not contain any vectors on L except for the origin. And now just take the ellipsoid, which is written here. This ellipsoid will have volume, which is at least the determinant or this product, which is at least n, and it gives you this bound that you wanted. So this is the Rogers proof. Okay. Questions about Rogers proof? This is Rafi's proof. So additional proofs that I will not talk about today. Let me just tell you why you can kind of things that you can improve on the Rogers proof. So the point that you could find a bit not satisfying the Rogers proof is that Rogers pretty much inspects only the n shortest vector in the lattice, and from this Rogers constructs an ellipsoid. But it does not make sense to interact only with n vectors from the lattice. An ellipsoid in Rn is determined by n square parameters. Okay, so it makes sense to have interaction. Each of them gives kind of one constraint. So it makes sense to try to interact with n square vectors from the lattice. For example, it is known from a century and a half more that there are ellipsoids in Rn, okay, that are integer free and have lots of points on the boundary. Okay, they have many contact points with the integer lattice. Let me explain to you how to construct an ellipsoid with many contact points on the boundary. I don't say it has large volume. Okay, right now we use number of contact points as a proxy for volume. We care about volume, but let's see how to get this in a very flexible way. So how to get ellipsoids with many contact points, okay, which are integer free. So the idea is, okay, begin with any lattice L, and then let's begin even with let's have a starting point for the algorithm, some ball which is L3, some little ball that contains the only nodes of vectors, and let's try to deform it continuously in the space of ellipsoids while keeping this integer free condition. So the crucial property of this our continuous evolution in the space of ellipsoids is that when our evolving ellipsoid, I call it ET, when it hits some non-zero at this point, it will keep it on its boundary at all later times. Okay? Or in other words, if you write this ellipsoid as AT x times x at most 1, so it means that if you hit the point x0, then you require that all later times AT x0 times x0 will be equal to 1 at all later times. So each time in this evolution process, which I did not specify it, but each time when you encounter a new lattice point, you get a constraint, linear constraint on the matrix AT. Okay, this is the process. Let me have animation for drawing it. So this, you start with this circle, deform it continuously, maybe this way, and you got more contact points, so you keep them on your boundary at all later times, and then you're done. And I claim that this process will give you at least n square boundary points. This is why, because just count dimensions. We said that each point gives you one linear function on 18, okay? You run out of, so the space dimension n square. So you can, as long as you have 1 degree of freedom left, you can move further. So you get at least twice as the dimension, many points on the boundary. Why twice? Because point come in pairs. Okay, so each time you touch 2 pairs because it's centrally symmetric. That's our construction. Okay, so we have many ways, very flexible. Any continuous process will give you n square boundary points, okay? And now, all we want is to replace this idea of having an ellipsoid with many contact points with an ellipsoid of large volume. That's what we want to do, okay? So the evolving ellipsoid is L3 and it has roughly n square points on the boundary, but how to estimate its volume? It's not clear at all. And in order to estimate its volume, we want to use the Poisson process heuristics. Okay, the Poisson process has, Poisson process has the properties that it's a collection of points in the plane. In each 2 domains, the points are completely independent of each other, and the number of points in a domain is expected to be its volume. This is a Poisson process. Okay, so you have one point per unit volume. This is the Poisson process. So let's see what happens if you take any evolution process, not particularly bad, just random evolution process, whatever, Brownian motion, and try to see what will be its volume. If, and our heuristic is, you should replace the lattice by a Poisson process and see what you get there, and then hope that you can transfer the result back to the lattice. Okay, so what would we get? So if you have a Poisson process in the plane, as he said, it has 1 point per unit volume. And the nice thing is that if you have the evolution process of the ellipsoid, you don't need to declare in advance what is the entire Poisson process. You can kind of sample the Poisson process on the fly. Whenever you encounter a new region in space, it's independent of everything in the past. So you can just flip coins and see, okay, do I have points in this region? Therefore, what it means that if the evolving ellipsoid, we know that it needs to encounter n squared points from the discrete set. In the Poisson case, in order to encounter n squared points from the Poisson process, you need to cover a total of at least n squared volume. You will not get that large volume unless you really, you not get so many contact points unless you cover that much of volume. Okay, so this is our heuristic why we should expect that if you have some reasonable process, then it will reach volume n squared. Now, there are many issues with this Poisson heuristic. For example, for Poisson process, you can find ellipsoid of volume infinity, which are disjoint forms, so it's not really, the analogy stops here and there. But if your process is simple enough, it does not use then you should hope that you'll be okay. Okay, that's and our ellipsoid will not just increase. You make sure, because you just have linear, you cannot make it just increase in directions. It could be that its volume expands and contracts. So it's not that if you reach some region in space, you have to go from it. It's impossible, but somehow you can hope that it will still work. That's roughly the idea of our construction. Okay, so let me explain to you how to do it rigorously. So we start with let's say that the lattice is fixed. Okay. In truth, I'll have two sources of randomness. One of them is the random lattice, and another source of randomness is will be a Brownian motion in the space of ellipsoids. But for now, let's think about the lattice as being fixed. So we have a fixed lattice L of covolume, the volume of the unit ball. And if you take a random lattice, then with good probability, it is disjoint of the unit ball. It didn't think the unit ball, but something slightly smaller to have some big probability. But this is roughly the unit ball. Okay, so dimension is large. So we have a random lattice of volume 1, which is roughly disjoint from the unit ball. Okay, and I start with this unit ball, little scale, and I want to deform it continuously in the space of ellipsoids. Okay, and due to lack of imagination, all I can think of is just Brownian motion. How could I grow the ellipsoid in the space of? I have no idea which process is better. Let's just take the Dyson Brownian motion. Dyson Brownian motion is just standard Brownian motion in the space of symmetric matrices. Okay, it's a famous process. The matrix, which is completely analyzed and everything is known about it. And the process looks like that. So you remember that the ellipsoid ET is determined by the matrix capital AT, okay? I begin with the identity. This is just one, roughly one. I begin with the ball, read ball, pretty much, and I just add white noise to it. That's all I do. I add just Brownian motion. But I have to stop. I remember that I need to, if I get a point on the boundary, I have to keep it for later times. So I define a stopping time, the first time when I encounter some point on the boundary. This is star 1. And then I continue in the orthogonal complement to the constraints. So in the highest phase of the process, I look at all of the contact points. I know that all I'm allowed is to make progress I need to have a linear constraint, so I'm allowed only to advance in the orthogonal complement to the constraint. So I take this white noise and I project it linear projecting the space of symmetric matrices to satisfy the constraint, and I continue this Brownian motion in the complement, and this tau y is when I get a new point, etc., etc., etc. Okay, so there are a few things to prove here. For example, y is AT positive definite at all times. It's not entirely obvious. It's true. It's true because it is integer free, so its volume by Minkowski's first theorem is bounded, and only
one to be using Minkowski's second theorem in this argument. You're going to go up to n squared. You're going to first go through n and then n squared, or you're going to go straight to n squared?
What don't get?
You're going to go to a random guy, run this Brownian motion, and improve
n squared.
n squared. I'm asking whether you're going to use Minkowski's second theorem.
No,
No, okay.
no.
So in other words, you never see the Rogers n. Okay.
Not at all. I just don't see it. I just say as long as it gives a freedom, continue the process. I don't see any.
Yeah.
Yeah, normal number theory. Okay, so yeah. But actually, this okay. So just the number of phases is finite. Actually, it's maximum. I mean, yeah, you can prove things that are not so hard. Number of phases is finite. Give some horrible bound, but it's just finite. And you stop the process when you have no place to go. But the projections is a zero projection. The space of constraints, you have too many boundary points on your ellipsoid, so that there's no way to deform the ellipsoid while keeping all these points on the boundary. So in the play, it happens when you have 6 points. So 6 points, the ellipse cannot change. Dimension n, it's a bit more. Okay, so this is our process. I said why it's always positive definite because if you have an ellipsoid which is integer free, by Minkowski's first theorem, its volume is at most 2 to the n times something. It's fixed, it's bounded, and the only way for an ellipsoid to degenerate to a hyperboloid or something is if its volume becomes infinite at some point. If its volume is bounded, you know that 80 will always be positive definite. Okay, that's the process that we want to analyze. Okay, so this is the process that we claim that would give you an ellipsoid of volume n squared. That's the simplest thing you could possibly write down on a paper, in a computer. Okay, any questions about the construction of the process that gives you the n square ellipsoid? This is the process. Okay.
Why do you take symmetric matrices?
Because an ellipsoid, so you're right that it could take non-symmetric. So an ellipsoid is defined this way, right? If you take a non-symmetric matrix, if you symmetrize it, it's the same ellipsoid. So A and A plus A transpose over 2 would give you the same ellipsoid. So why would you look at the non-symmetric part? Just look at the symmetric part. All information is there. No reason to look at
And
that.
have the norm, right? I mean, you have to, all the eigenvalues have to be positive. All the eigenvalues have to be positive. Otherwise, you get something that's not an ellipsoid.
Exactly. So I'm guaranteed if you have an evolving ellipsoid, I'm guaranteed that it always remain an ellipsoid, do not degenerate to this, do not become any other surface. Why? Because even its volume is bounded. So this is the difference between the Lattice and Poisson process. In the Poisson process, you can have ellipsoid of arbitrarily large volume that are disjoint from the Poisson process and things like that. But for the Lattice by Minkowski first theorem, the volume of the volume mechanics is just bounded from above by some number, which means that I'm guaranteed not to leave the space of ellipsoid in the process. So the matrix, the symmetric part of the matrix will surely be positive definite. No question.
Is the lattice random? I kind of missed it. The lattice is random.
Okay, this looks like lattice. I can start with, and so I just for pedagogical, I want to separate two. So you are right. Your question means that you understand. So I just want to separate the two sources of randomness. So this works for any lattice. At the very end of the proof, I say, it was a random lattice all the time. Okay, but this so far everything works for any lattice. Okay, but it will be a random. In your head, think about the random lattice.
It will be random but static. It won't. The lattice will not change.
Yeah, exactly. Random and static, and I put it's just my choice. My choice is to have the lattice random and static, and to have the ellipsoid evolving. That's my choice in the book. But of course, you can formulate you can do all the randomness in one side, easily, if you prefer. But it's a mess in your head. You do this way. More questions? Okay, so we have a well-defined stochastic process. How complicated could it be to analyze it? Of course, actually, it's that complicated. Indeed, it's not that hard. So actually, I don't even run the process till time infinity. I run it till a very specific time. I just stop the process. So the process will give me all the time an L-free, integer-free ellipsoid or L-free ellipsoid. I prefer to stop it in this particular time. Okay. Why is that? Because we will see that I can compute what's the it absorbs points on the boundary, right? We can compute what's the rate at which it absorbs points on its boundary, and as it turns out, the number of points that you absorb by time t, it grows. It's bound is at least for short t, it grows like exponential in t with this large constant here. So this means, and I want to stop when I get n square points of the boundary, right? In my head. For some point, the heuristic detect everything. So when I get n square points of the boundary, I expect to have volume n square. So this number, if you plug it here, you should get n square. I hope it's true. Okay. So that's why I stop at this time. Okay. And the claim that we need to prove is that with the above process, with probability 1/2, let's say, at time t, this t, the determinant of AT is at most n to the 4, right? Why do I want n to the 4? Because the volume of the ellipsoid is 1 over the square root of the determinant of the matrix, so 1 over n to the 4 of the determinant means n square volume. This is what we want to prove. Okay, that's our goal now. Okay, now let's try to understand our process, this evolution process in the space of matrices. So it's not pure that, I mean, okay, there is the Dyson-Brownian motion. Here you just add white noise and the matrix becomes indefinite very quickly. What we have is some modification of the Dyson-Brownian motion, okay? But it is still a martingale. So this martingale means that whatever you add has zero expectation each time. And when you have a martingale, its behavior is governed by its quadratic variation, which means it's in the speed that it, because the expectation of u is zero, what is important is how it, what's the speed at which it goes up and down. And the quadratic variation of this martingale is bounded by t times the identity matrix. The rate of growth of the quadratic variation is most the identity. Okay, because the stochastic maybe. So if you like stochastic differential equations, AT has this the following evolution. So I take dWt and I project it on the space of allowed movements. Right? This is the evolution equation, and that's an orthogonal projection. So in all directions, it's smaller than the evolution of the Dyson-Brownian motion. And then there is a very nice fact that is attributed to Bernard Morin. And this is a very general thing about martingales. So if you have any martingale in Rn, or in R, even in R, it's interesting.
About Brownian motion, for me, it was a metric or Riemannian metric on the space of.
Yes, it's very good. So it's even Euclidean, even better than that. So the space of matrices is equipped with the scalar product of AB. It's just trace AB. So it's even a Euclidean metric. This is the, I don't need a transport, I just put it for myself, but it's symmetric, so I don't need transport. That's the simplest possible thing. This is, you have a total base of motion, each of them has Brownian motion. This was Dyson film and Dyson, that's the process. And whenever you have this martingale, that's a very nice fact, which is not too fast, the Brownian variation. You can express the martingale as an average of two standard Brownian motions which are dependent. You have two dependent Brownian motions, WT1, WT2, with average equal that given stochastic process. Okay, for example, if AT is just constant, suppose it has zero quadratic variation, does not change at all, then you can take some Brownian motion, take its minus. These are two Brownian motion dependent, but two Brownian motion, and the average is zero. So that's one example, and if it's a complete Brownian motion, take the same, WT equals WT1, 2. So, but in general, if you can visit average of two Brownian motions, that will be useful for us in the analysis. Okay, now, as I said, if you have that's a Brownian motion, that's completely understood.
The standard because you were using, you had this bound on the variation that sort of allows you to present.
Exactly. So if you know that the rate of change of variation is what identity, it means that your martingale is an average of two Brownian motions. The proof is just really very simple. So you have this pi t, okay? Plus or minus identity minus pi t. So these two things, I think it's somewhat. If you do either plus or minus, get a Brownian motion. That's the. And the average is the original thing. That's the proof of More's corollary. And this would help us analyze things. For example, okay, if I have a pure Brownian motion, Dyson, then I know that at each time you get a GOE matrix, and everything, you only need the crudest, let's do the very crude bound that you know that the norm of a GOE matrix is most a constant root of n. Okay, I'm embarrassed to say this form of harmony, you know so many things, but this is the most crude bound you can do in epsilon net. You get this trivial bound. This is already good for us. Why? Because this means that if you look at our process, what's the probability that it deviates from identity? A0 is identity. Identity by more than something, okay, it's a sum of Brownian motions. You do the union bound. It was the probability that each of them would be large. This is very small. So it means that typically, you already get that your ellipsoid ET at the times that I care about is sandwiched between two constant Euclidean balls whose radii have ratio which is very close to 1. So the ellipsoid does not do much, right? Just perturb a little bit and that's all. This is the trivial corollary of this Morez lemma. But it's still not good enough for us because these ratios, we need to raise to the power n to get something about the volume. And this will become e to the root n. When I don't want to square it. I mean, to take power n of that because it's one over root of it. So it's not good enough. We need to be more careful. Okay, so let's analyze really the determinant of this evolving ellipsoid, ET, and better to take the log. It's positive definite matrix. Just take the log. Log that is a beautiful, beautiful function on the cone of positive definite matrices. It's a concave function. And for example, if you just look at the white noise, that's Brownian motion. If you start this process, you know that, because it's concave function, if you add the martingale, it will go down in expectation. So the average at two nearby points is smaller than the value here, it's concave, so it should go down. So you are kind of guaranteed that for martingales, an expectation goes down, it's already very promising. And the rate at which it goes down, okay, so for the Dyson one, it's minus n squared over 4, kind of. And for us, it will be, so we just, it's not so complicated, just try to understand in which directions the evolution goes, and you kind of lose whenever you evolve in a lower dimensions of space, so you pay a fine for the number of contact points. So I get this upper bound, so the expression of log det for a matrix. So this factor is the same as this factor, n squared over, okay, it's a half of, okay, but this factor is what I get from the pure Brownian motion part, and I pay a fine, which is the number of contact points. Okay, so what remains to be done, if you believe me, is to bound the number of contact points. And then, okay, I can compute for a given point in Rn, what's the probability to be absorbed by this evolving ellipsoid. And then again, I use my trick. So I have this evolving, I have a fixed point. One will be absorbed when this martingale goes below 0. Okay, but this is again an average of two Brownian motions, and I can compare the probability with what you get for Brownian motions for some Gaussian integral. Okay, so this phi is the error function. So what I get is that the expected number of points on the boundary of the ellipsoid is the sum of the probabilities, and each of them is bounded by some error function, phi of something. Okay, and I only look, so what I'm going to do, I need to sum these probabilities over the entire lattice, but I know in advance that I only care about a thin spherical shell. I know that the ellipsoid is very close to the ball, so only I care about the only reasonable contact points would occur in some thin spherical shell. So I pay some error to move from all of the lattice to just thin shell.
Was I'm a little confused, right?
I'm a bit out of time, so how much time do I have? Just 3 minutes. Okay, I'm aware of the time. Just yes, no, please.
So this ellipsoid, it's evolving in this lattice. So the
it evolves in Rn.
No, but the dynamics depends on the lattice because when you hit the point of lattice, so the ellipsoid is dependent on the lattice.
Yes,
but it feels like you've applied the single formula here as though the lattice and the ellipsoid are independent.
So I can bound my main trick. My main trick is this fact. So I can express my process. If you want, I embed my ellipsoid in the union of two ellipsoids, which are kind of Dyson ones. So that's my trick. That's my main.
That ET is not the original. It's not actually the ellipsoid you construct. It's one of these two.
Pretty much yes. So in both estimates, I use that thing. Yeah, one of these things. That's why. So that's why I get the Gaussian, just plain Gaussian, and not the. Yeah. So I get So what I get from that for any lattice in the world, if I run my process, the expected number of contact points is at most the sum over all lattice points in some ring of the error function of something. Okay, this works for any fixed lattice. And now I introduce the randomness in space of lattices. Okay, now I say this is true for any lattice, so let now L be a random lattice of covolume, right covolume. This random lattice with good probability is joint of the unit ball, so like it's allowed. And then I say, for if I take the expectation of the right-hand side for random lattice, well, this is exactly the Zegel summation formula. This is the left-hand side of the Zegel summation formula. So I replace this impossible sum over lattice. After explaining, it becomes an integral of a radial function in Rn. Okay, that's easy thing, right? The integral of radial function in Rn, you just do probabilities, you have one-dimensional integral, you estimate it, and you get that for random lattice, the integral of the contact points, it's most what I told you, and you plug in this thing, and you get this is how you finish the proof. Let me just remark, so we really use only the first order Zegel summation formula, nothing more complicated. maybe we can squeeze a log. I couldn't do it, but by using something higher moments. What we seem to be able to do is we now writing this paper with Gava, it was mentioned earlier. So we can combine the cyclotomic fields with this and maybe get log in some dimensions. That's the yeah. So this is all I wanted to say. So for going over there.
How does this square with the fact that the concentration is so close to the mean? It's what you're battling. So right? This is what the problem's hard, is that the mean is giving you the same answer over time, and you're trying to find.
Okay, so we look at the function number. The function is really close to the. Okay, so we look at the spread of lattices and we have the function lambda 1, let's say, length of the shortest vector. And it's true that randomly you get certain value, but what we do, we don't just take a random value, we kind of look on a local hill. So we start with a random value and we climb a local hill and reach n squared. That's our process. So the fact that typically you're right, for the random lattice concentrated, you get n squared, and just get constant, sorry. But after climbing this local hill, you get n squared. That's what we do.
Why do you think it's sharp?
It looks okay. So maybe actually no. I think it should be. I would not commit. You need to believe in a few things. You need to believe. Okay, I don't know where do we stop. So first of all, you need to believe that there is no algebraic construction of a lattice somewhere in the cast that out for. So we are there. This is at least, I don't know, 20%.
I think these guys are in the bulk.
What? You think
not in the cast? Yeah.
Okay. Another thing you should believe is that that the landscape of this function of lambda 1 is just many local hills. Yeah. It's like of this function in high dimension that we have many local hills. Okay, maybe. Okay. Then you need to believe that these local hills are kind of independent of each other. So just like, and you know, okay, for a single point, you kind of know that you have this exponential law of lambda 1. This is known. Yeah. So if these are, and then you say, okay, I have like the number of experiments that I have is n squared log n, e to the n squared, and each of them is exponential. That's the heuristic argument for that. You know, it's really, I mean, it could be completely bogus, right? I'm not saying that it's the truth, but it's a heuristic argument which gives you a result of believing n squared. Thanks a lot.
So what's the probability of finding this guy?
99%. It depends on the constant. If you optimize.
Actually, could you run this thing numerically?
Yes, so the Zamponi, the physicist, so he told me that they now run some project of computer simulations, and let's see what the outcomes of this project are. So there are also variants. So my process was this is to prove. So actually, the process is easier to analyze. I just want to have a proof, but there are processes that make more sense in terms of the problem. So I mean, if you see many points in some region, maybe weekend random walk in some directions, else. You can in the run simulation you could do all sorts of things and. Maybe you can get a log factor from there, I think more sophisticated things, or even more than a log. It would be really amazing if you get more than a log.
But isn't it true that if you, in the physics, like even in 3 dimensions, if you actually take a set of balls, then and you do it, then you kind of get stuck at a much smaller number than the optimum. Is that a relevant issue in when
they say so? They say so, yeah. They say so that exactly. They say so that somehow it's like discontinuous. You want to? It's not. Yeah, so you reach a local minimum, which is not. So let me just remember, dimension 9, even in the space of lattices, how many local minima you have? They found 2.2 billion, this I remember. So maybe there are a lot of them. So to reach a stationary point is really easy, and I'm not sure, I didn't really try with an actual sack.
I just remember that in 3 dimensions, there was a lot of discussion of another number which is physically more important, because that's a number that, I mean, you mentioned some material that changes as a phase transit, but there was another number like 60% in the physics, which is where things, where it's more natural, where you land up being the maximum. Not the ultimate maximum.
But all materials pretty much get the 74%, so I'm not, okay.
Well, that's.
I mean, really,
They have a crystal structure for this.
Yeah, it's a crystal, right, yeah, for crystal. Yeah. So I don't know what's not there. It's all something that are not there. Yeah, but right, the amorphous gas philosophy, right? So if you kind of cool down and it does not crystallize, so if it crystallizes, it's something. If it's in the glass phase, they say the glass phase. There is a phase called the glass phase, which is like liquid but very slow swimming. So in the glass phase, you're right. This is something. But it's 60% in the glass phase, yeah, that's what we said.
No, I just remember
Could be.
in dimension 3, I was once at some workshop, and they were highlighting, it was Hales and some physicists. That number didn't come up as much as another universe. That's all.
Interesting.
In dimension 3, I'm talking.
Okay. Maybe for the glass phase. Okay. Thanks, I didn't know this.
More questions? Both again?